Hi, how's it going? In this video, we're going to take our scene and add planes. Here's what we've got at the moment. Pretty straightforward. We have a bunch of spheres. The only thing I've done to modify it from the previous video is if we go to the engine, or if we go to the scene, then I'm also keeping track of whether the scene is up to date. At the moment, we'll say yes, it's outdated because we want the engine to take a snapshot of the data and upload that. Let's just move the camera back a little bit. Okay. Now what we've got here in the engine is when we go to draw the scene, we test whether the scene is outdated. Okay, and if it's outdated, then we update the scene. What this consists of is searching through all the objects in the scene, adding them to the sphere data texture, and uploading that data. So instead of uploading the data every frame, we are uploading it every now and then. It's completely up to us. Okay, so what we need to do is we need to add spheres. But to start with, I'm just going to explain how to do it mathematically. Hi, so here's the situation. We have a camera, which we'll put at some position, and the camera has a start position A, of course, and it's shooting a ray at some direction. And what we're doing is we're hitting a plane. Now a plane is defined by kind of two things: a point, which I'll put C for the center of the plane, and the plane's normal. And what the ray is doing is it's tracing forwards and hitting the plane at some point, okay, which we'll call P. So as usual, we have two kind of fundamental equations. We have a ray equation and a plane equation. Now the ray equation is saying that the point P is equal to the, doesn't matter, we'll put lowercase a for the start point of the ray plus t times the direction. And then the plane equation is saying, well, if we take the direction vector from the point, from the center to the point, like that, and we take its dot product with the normal, that should be 0. So then we can put that information in. We can put this information in here. Remember that CP is the center minus the point. Okay, we put in the expression for P, so we have, let's do the same thing that we did before. So we'll have A minus P D. Okay, fair enough. And now let's use the dot product properties to split this up. So we have two things. We have there. And remember, our goal is to solve for t to find the length along the ray at which it hits the plane. So now this equation can be solved. What we do is we subtract the first dot product from both sides. So subtract it and then divide by the multiplier, which was this dot product. There. And there we have it. There's just kind of two caveats to this. Number one is we want to make sure that this denominator is Yeah, there we go. We want to make sure this denominator is non-zero. Okay, we don't want to divide by 0. And then number 2 is we want to make sure that the dot product between the direction and the normal of the plane, we want to make sure that's negative, which means that those vectors are pointing at each other, not in the same direction, but towards each other, because we want the plane to be pointing towards the ray that's shooting at it. Okay, so there's that. But then issue number 2 is, well, we don't want an infinite plane, we want some constraints. And then later on, when we do texture mapping, we can also use this information. So what do we have? Our plane kind of shoots across, and we'll go up here, okay? Hits at some point. But another plane could shoot across and hit outside the plane, so another ray. So how do we know whether a plane, how do we know whether a ray is hitting a plane inside its constraints or not? Well, for that, we have 2 important vectors. We have a tangent and a bitangent. And then we have the center of the plane. So the first thing we do is we've got the value of t, we've solved for that. We can then put the value of t into this equation, start position plus direction times t, to get the point inside the plane, up to kind of float error, so within some margin, but pretty close to inside the plane. And then we calculate that vector CP from the center to the point P. And then this diagram isn't so good, but I'll try to kind of exaggerate it a little bit. Okay, we want to know how far is this in the tangent space. How far is this along the tangent, this point? So there'll be like a left bound and a right bound. And we also want to know how far across is this, how far is this along the bitangent. That measurement is, we're going to call that V. Okay, well, if you've done any linear algebra, you know this is very similar to a vector projection. As a matter of fact, it pretty much is a vector projection. So we say the length u is we take that vector from C to P and take its inner product, its dot product with the tangent. And that will indicate how the component of this vector, which is parallel with the tangent, how long is that, basically? And same sort of thing for V. So we take CP and dot product with the bitangent. That will give us the range V. So for instance, if we look at this point outside and we take the direction vector and we project it here, then that will be within the range for V, but it will be outside the range for U, because it just stretches out too far. That's too far along the tangent. Okay, so that's the basic theory. Now let's get in and code it. Okay, cool. So you watched my informative video. Now let's get to the action. So we'll go create a new class called plane. And here's how that plane works. We have everything we would expect. The 3 fundamental directions inside the plane, as well as some constraints. We don't want an infinite plane, we want to constrain it along the tangent and bitangent, as well as a center and a color. So this is pretty much the standard thing that we're used to. No problem, very similar to a sphere. Now what we need to do is, I'm just going to go to my scene and I'm going to create a plane, just a ground plane. I could randomize this and create a bunch of them, but some of them wouldn't be visible. So I'm just going to create a ground plane. These planes are going down to a minimum Z of -5, and they have a radius of 2 at the most. So the ground would be, yeah, I'll just import that. Okay, excellent. The ground would be at a Z of -7, I guess. We could raise it, it would be cutting through some of the spheres. It really doesn't matter. Okay, so just super quickly, because we moved the camera a bit, so let's just have another look at this. Okay, so it's the same scene, but the camera's moved backwards a little bit. This will make it a little bit more visible. Excellent. All right, so that is it for the scene. Now let's go to the engine. Okay, so we're going to create the resource memory, and I'm just going to generalize this. I'm going to call this object data. So what we could do is we could create a texture for the spheres and a texture for the planes, or we could load them both into the same texture. Now, loading them into the same texture does waste some storage. For instance, it takes a lot more information to store a plane than a sphere, so we're going to have about 3 wasted pixels for every sphere. But I'm not too concerned about this, because in my experience, what I'm finding with my system is that it is more limited by the number of textures that it can bind than it is in the memory amount of those textures. So we can, the system I'm working with is happier to bind a really large texture than it is to bind a bunch of small textures, even though that wastes some space. That's just the way it is. So I'm going to work with that. So what we'll do is we'll have, it doesn't matter, I'm just making these names more descriptive. We're going to have up to 1,024 objects, so that's spheres and planes combined, and we're going to have a maximum of 20 attributes for each thing. Okay, so we'll just go ahead and create that. Okay, excellent. And then we're just going to call this an object data texture. And load that in. Okay, and as we can see above, we are going to use 5 pixels for each of these. Cool. Excellent. So now we're going to have to change the record sphere. I'm just going to paste this in. So now we're going to have to change the record sphere to reflect the fact that the data buffer that we're sending it to has 20 attributes for each sphere. So in other words, oops, the stride is 20. And that is reflected in this code here. Oh, what's going on here? As we can see, for each new instance of I, we're going to jump ahead 20 spots and allocate some new memory. We're not using all of it. It is what it is. Okay. Similarly, we can make a function to record a plane. And yeah, it's a lot to put on the screen all at once, but hopefully we can see we're just loading in the center, then the tangent. So we're just loading in this data in the same order that we described up above. And if this is a little much, remember, as always, the code is always linked down below, so you can jump in, you can have a dive around. You can have a look around. Okay, cool. So, update scene. So what am I doing? We're going to load in the spheres. Yep, good. And then we probably want to tell the scene. So I haven't created this yet, but we'll probably have a plane count variable. And we're going to load in the length of the planes. Then we're going to go through the list of planes. At the moment, there's only one, and we're going to record that. But taking into account the fact that the planes and spheres are written to the same buffer, we're going to add an offset here, which is just the number of spheres which have already been recorded. So if we have well, we've got 16 spheres here, right? So we go 0 to 15, then we add in 16 plus 0, so then the planes will start at instance 16 and go on from there. Excellent. All right, so then we just change this. This is, we're going to bind the object data texture, 5 pixels by 1024, and we're going to send in the object data. Fun fact, I was working on this before and I accidentally sent in the object data texture to the object data texture, if you know what I mean, and it was creating all sorts of errors. Actually, it wasn't. It was just drawing a black screen and no errors, which is even scarier. Okay, so prepare scene. We just need to update this. So we're going object data texture. Great, great, great. Yep. Everything here looks good. Okay, so what we're doing is this should all be fine. We are setting everything up and then we're rendering. But then the question is, how are we handling the data on the other side? So let's jump over to our shader. And to start with, we need to define a plane struct, because we haven't done that yet, but it's pretty much very similar to what we've done before. So we just declare all of these vectors, then the constraints and the color. Excellent. Okay, so also instead of spheres, I'm just going to call this objects. We're going to need a version of the render state, a version of the hit function, which also works with planes. Okay, that's looking good. And we're going to need a function that takes an index and unpacks the plane data. Okay, good. Right, so let's go to this function here. Okay. So what we did is we test all the spheres. Now we'll test all the planes. In this case, there's only one. But we just need to be mindful of the fact that there are what am I thinking? Mindful of the fact that the spheres and planes are packed into the same buffer. So what we're going to do is the first plane will continue from the next, from the last sphere, basically. Oh yeah, I forgot to define that. Okay, so we just go back up to the top. We've got sphere count. We're also going to have plane count. Awesome, good. Okay. Alrighty, so again, we're doing exactly the same thing. We're just going from a different position in the buffer. We unpack the plane from that position and we run the function on it. Cool, so now we just need to create the function to unpack a plane and then hit a plane, basically. Oh, while we are at it, I'm gonna change this from spheres to plane objects, so we're getting it from our common buffer. Okay, cool. So if it helps, I'm just going to paste this in, just to be mindful of the memory layout. And then we can go ahead . Okay, so nothing too crazy, just a whole lot of work. We progressively load pixels along the horizontal line of the texture that we're up to. And it follows this kind of setup. So the first pixel has the center position, X, Y, Z, and then the tangent, and yeah, so on and so on. I won't go super in depth in this, but we can see briefly that it's doing nothing unexpected. Okay. So now we need to make a hit function for the plane. Okay, cool. So remember I was saying that we need to check that the denominator, it shouldn't make a difference. We need to check that the denominator is non-zero and negative. So that test is done here ahead of time. And then we solve for t. Then we check that we are within our bounds, that we haven't got a closer object obscuring the fragment. Then we get the point, which is kind of inside the plane. So again, that's the start of the ray plus t times its direction, puts us at that point inside the plane. And then we get the direction vector inside the plane, which is the test point minus the plane's center. And then we get the coefficients u and v, which indicate how far along the tangent that point is and how far along the bitangent that point is. Then we can just go ahead and test that in the expected manner. And yeah, get the result, return it. Awesome. So let's just test this. Okay, fair enough. Plane object has no radius. What have we done here? 134 in record sphere. Am I accidentally calling the same thing again? Yes, I am. Psych. Okay, that's better. Awesome, there it is. So see, we have a constrained plane. It doesn't stretch forever. And also, we almost get for free the texture coordinate inside the plane. That's very cool. And this is a very straightforward case, but we could have a plane of any orientation and this would work. Anyway, I hope you had fun. And yeah, I'll see you in the next one. Bye.